Hi everyone, how's it going? This is Siri and I'm back with another PyTorch video. And in this video we're going to be continuing our discussion on the learning process, and we're actually going to be going over the implementation of what we've talked about in our video on parameters and loss functions. And this isn't really like a real neural network, although it does follow the same lines. It does go along the same lines as that because, you have your data, you're trying to model it, you're trying to represent it using a mathematical function, and we're using tensors here too. And the only difference is that this is just, we already know from the start that this is, a linear relationship between the input and the output, and we're just seeing how the model is going to figure that out. And even neural networks are just like Python classes, right? That's what you're going to be defining. It's nothing like magical or anything like that, but we'll tackle that when we get there. And even though this is just a linear model, it's not far off from what actually happens. And we're just taking things one step at a time and starting out simple. Okay, so let's go over that implementation of our model. And if you are confused or want some more clarification, or just want a refresher on what parameters are, what a loss function is, I go into that in good detail I went into that in good detail in my previous video on parameters and loss functions. So you feel free to check that out if you want to. But right now we're going to be defining our model. Okay, and don't get scared. This is just like a mathematical model. We're modeling a mathematical relationship here between the input and the output. And in our model, the parameters will be PyTorch scalars, so they're like 0-dimensional tensors. 1D tensors are vectors, so just scalars would be 0-dimensional. So let's define a function called model, okay? And, okay, this is a markdown cell. So let's just call this model definition and say def model. Okay, it'll take in 2 arguments. Those 2 arguments are the input, the weight, and the bias. Okay, your model needs that information in order to decipher out that relationship between that and the output, right? That's how the relationship is set up, right? It's set up as y equals mx plus b if it's a linear relationship. So if they're related linearly, we're going to need a weight component and a bias component. And I also talked about weights and biases in my other video, so once again, feel free to check that out. Okay, but this sums it up nicely, right? We have y equals mx plus b, where y is our temperature in Celsius. And once again, we're continuing our temperature conversion sort of problem, where once again, the temperature in Celsius is our output, and the unknown temperature, the temperature with unknown units is our input, because that's what we're reading. Okay, so let's define a model that's going to take in our input of temperature of unknown units. We're going to have a weight and a bias. Okay, so let's return, the y equals mx plus b. So w is the slope, tu is the x input, and we're just going to add our bias. Okay, so you might be wondering how we can multiply these weights by this input tensor. We're going to be using broadcasting for this. And although this is a scalar, you might be wondering, well, why do we need broadcasting for it? This is a scalar, but it's like a tensor, right? It's a 1 element, it's a single element tensor, so we're still going to need broadcasting for this. It's going to be a pretty easy broadcasting, but yeah, if you aren't familiar with broadcasting and tensor operations, you might want to get familiar with those, because we're going to be using that, we're going to be applying it, and I do have a few videos on tensor operations, what tensors are, why we need them, and also broadcasting, which is just how we, you know, add tensors or like perform arithmetic tensor operations on tensors with different shapes. Okay, and yeah, so that's our model. It's pretty simple, once again, because this is a linear relationship. And yeah, so let's talk about our loss function. So our loss function just tells us how far off is our model from the actual output. So for example, if we scroll up here, and the actual data could be modeled with this function, but our model thought initially, or maybe like a few iterations in, maybe it was still wrong and thought it was x plus 2 when it should have been 4x plus 9. How is it going to know that it's wrong? Well, it's going to check out what's the difference between the 25 that it should be and the 6 that it got. So this is the 6 is the predicted value, and 25 is the actual value. And so the difference between them, and you know, either doing absolute value or squaring it, could potentially give you the value of the loss function, which we are trying to minimize, like I said. And if this is all sort of new to you, you know, like updating parameters, changing them, trying to find the best parameters, that's all good information that we need to know that I covered in my parameters and loss functions video. Okay, so yeah, so it tells us how far off our model is from the actual output, and we need these to be parameters, because the loss function is based on the difference between the two, right? So we need a way to tell our model that, hey, these are the two pieces of information that you need. You need the predicted value, and you need the actual value, and we need a way to pass that in, right? So like, we need a way to tell the model that this is a predicted value, this is the actual value, and that way is to pass in parameters, like you may have imagined. And so when we define our loss function, so we are, you know, we define it in the same way. We define a function called loss fn, so fn meaning function, and we have TP. We can call these parameters whatever we want, right? When we actually call the model, or call the function, right, that's when we pass in the actual values for these. We're just defining them. These are just the model definitions, the loss function definitions, and you'll see these definitions a lot, especially when you, you know, go through your own like projects. You'll see a bunch of definitions, and you'll probably see, you know, the actual applications of them in either another file, or probably you'll have to do it in your own command line, right? So we can have TP, okay, standing for temperature predicted, or TC, which is the temperature in Celsius, which is, you know, the actual output of the model. And so now we're dealing with 3 temperatures. The first one is the unknown unit temperature. That's the input that we initially started out with. 2, we're dealing with the output, the actual output in Celsius, what that unknown temperature, the temperature of unknown units looks like in Celsius. So that's our relationship that we're looking at. And we have a predicted value based on that linear relationship that we think it is for the moment. So we have a predicted value. And so maybe I want to punish the values a lot if they're extreme values, and you want to punish them, you know, once again, like I wrote here, the model is going to get that message that it's very wrong if you use the square of the difference instead of the absolute value. And so, yeah, okay. So let's say squared differences, or diffs, is equal to, let's just do the math here. This is very transparent. That's what I want you guys to understand here. We're doing this simple function and simple linear relationship. We're not jumping into the neural network yet, because I want to make this process as transparent as it can be. Like, what's going on? What is the loss function? It's telling us how far it is from the actual output. What is the model? What are we doing? Okay, what math is actually going on? Or relatively speaking, right? Because we have, some nonlinear components that we're going to be adding in later. But, we have squared differences, and let's take, like the way we defined it up here, it's the difference between the predicted value and the actual value, which is, the Celsius. Right? Our input is the unknown. And we are going to multiply it by... Actually, we're going to square it. That's what this means. So we square it. And we're going to return the squared differences. And I'm going to add this little thing at the end, and you might be wondering why. So dot mean. Okay, so look here. TC. What is TC? TC is a tensor full of values in Celsius, full of temperatures in Celsius. This is a Python list, but we convert it to a tensor here. This is a PyTorch tensor. Okay, so TC is a PyTorch tensor. TP will also be a PyTorch tensor because those are the predicted values. And what else do we have here? Yeah, TP and TC. So when you subtract two tensors of the same shape, right, we get a tensor. We don't get a scalar. We don't get a scalar value, and if it was a scalar value, then we would just return that. But our loss function, returns to us a single value that we can use to, determine how much we need to adjust our parameters. Okay, basically the purpose of the loss function. So when we take the mean of this, what we're doing is that we're taking the mean, or the average, of all the elements in that tensor. So that's where we get that single value that we can use. Okay, so when we take the mean, right, that's, pretty representative of the entire tensor that we get when we subtract it and square it. Once again, here we're doing this element-wise, so all the elements are squared differences, right? So when we take the mean of that, we get one nice value. Okay, so this is the scalar value that we want. Okay, good. So we also talked about in our other video about initializing parameters. So our model is not going to know the best parameters at the beginning. Okay, then we don't need to train it at all if we already know the relationship between the input and the output. Okay, we start off with completely random parameters. So our parameters in our linear mathematical model are the weights and the biases. And so maybe, once again, I'm coming back to this example here that we have at the top. So the actual data is 4x plus 9, and our model thinks it's x plus 2. Maybe this is the initial round. We didn't even start training it yet. We didn't even tell our model one single value for our loss function. We aren't telling our model anything because we're just starting out. And the initial value for our slope and our y-intercept, or in other words, our weight and bias, is 1 and 2. Okay, so that's what's going on here. And once we figure out that we're wrong, once we figure out, hey, based on this loss function, we are very, very off. We're 19 units off. So we're going to adjust our parameters again. So thinking back to our best fit line, maybe that will put things into perspective, right? We start off with the line that doesn't at all represent our data, and we're trying to find the best slope and the best y-intercept that will at least like as accurately as it can model that data. Okay, so we do that, and let's initialize our parameters now that we know why we need to. I also go into this in more detail in my other video once again. So initialize parameters and invoke the model. Okay, so let's do that. And you know, we're going to need PyTorch for this. This is, after all, a PyTorch video. I know we haven't gone into that much coding in the previous videos, but we needed to get that theory down and work our way from the ground up. So, yeah, let's import Torch finally. And now we're actually seeing, well, not now yet. Once we get into the more complicated stuff, we'll see the real power, the true power of PyTorch. But here we're just, you know, finding a way to deal with our tensors. Okay, because PyTorch has a way of creating tensors once again. Okay, so we're passing in like nothing. So those are our arguments to, you know, the ones. And B is going to be zeros. And so these are the default values for the weights and biases. Okay, we're creating a tensor full of ones, full of zeros, and this makes sense, right? You know, our default y-intercept is 0, so it's going to pass through the origin. It's not going to do anything fancy like, you know, like do like have our y-intercept be 4 and have our slope be like 52. No, our slope is just 1. It's just y equals x plus 0. Okay, so this is what we're doing here. Y is equal to x plus 0. And this is wrong, right? We all know that this is wrong, but we need an initial value that our model can work with and find the loss from. Okay, so that's what we're doing here. And when we run that, if we take a look at w.shape, right, doesn't have anything, and b.shape, okay, same thing here. Okay, so let's say TP. However, if we do, you know, if we do find W, it's just 1, right? It's a scalar value. Like I said before, this is a scalar value. You know, these are both scalar values. Except, you know, they're in tensors, right? So, okay. So let's invoke our model. So let's call our model on some data. Okay, so we have TP. So these are our predictions, okay? Our predictions come from the output of our model, okay? And what do we pass into our model when we call it? Well, I know it might look like we're just like literally copy pasting, you know, this here, but, you know, we already defined TU. If you want me to copy paste it, maybe if that makes it easier, then that's fine. But maybe we should... No, I'm not going to copy it because then our Jupyter Notebook's going to be double the length and we don't need that, right? We already have it. Okay, so this is TU. Okay, well, we already defined TC. We did not, however, define TP because we didn't call the model yet to get any new predictions. So let's say TP is equal to model. Let's pass in our, so what do we pass in? We need to first pass in our TU. Okay, this is just the parameter name. This isn't the actual TU, if you know how functions work, right? I could have called this like unknown temperature, right? I could have also called this unknown temp, right? It doesn't matter, but I'm just gonna keep it like this for consistency. So instead of writing weight and bias and unknown temp, let's just keep it as is. Okay, so let's say TU, and W and B. Okay, and let's say TP. Let's print it out and see what we get. We didn't run this. Okay, so TU is not defined. Okay, maybe it's been a while since we ran this. Let's run this again. And we already ran that. Okay, so okay, good. So now we have some predictions. We have some, 35.7 degrees, 55.9 degrees, 58.2 degrees. So that, after we pass in our TU, that's our expected, output. So let's see. Let's look here. So it's 35.7. It's definitely going to be way off. Yeah. Yeah, it's basically the same thing as the input, right? 35.7, 55.9, 58.2, is that what we got? Yeah, this is what you should expect. Our weight was 1. Our bias was 0. And our equation was y equals x. So what did you expect? Our output is the same thing as our input, and we definitely know that is not true because the temperature that we were reading originally on our thermometer is not in Celsius. So it's not going to be the same as the output. So yeah. And yeah, so now you have a feel for, how we define a model. It's just a basic, not that much code, right? But, it's worth it to, just sit down and go through, what's going on. How are we defining this loss function? How is this working? How is this working with our data that we already have? That's already, assuming that it's already in the form of a tensor that we can work with. And how do we initialize these parameters? Why do we need to initialize parameters? And how we call the model on our data. Okay, so in our next video, we're going to be talking about, and you can look forward to this, we're going to be talking about how we estimate that W and B. Right now, it's just 1 and 0, okay? They're bad, they're wrong, and they're horrible. How do we make them perfect? How do we make them at least close to perfect? How can we make that line, that equation of a line, how can we make that representative of our data that we have? So in order to do that, we need to make sure that our loss function reaches a minimum. So, we have a function that, represents that loss, and we want to have the lowest loss. We don't want to have, we can't expect to have 0 loss all the time, but we want to have close to 0 loss, and we're going to be going through how we actually update those parameters in order to do so. Okay, so you can look forward to that for next time, and I hope you learned something new today. I hope you got more intuitive understanding, although we're not done just yet, right, because we need to finish this example. So I hope you learned something new about the learning process, this whole machine learning process, and I'm looking forward to seeing you guys in my next video. Don't forget to like, comment, and subscribe.